Hello and welcome back to the lab. On the bench today, we have the Hewlett-Packard 419A DC Null Voltmeter. The 419A was widely seen in metrology and standards and calibration labs throughout the 1960s and 70s. Had numerous applications in standards and calibration. Was also very useful for general purpose instrumentation. 419A has a zero-centered meter with a -1 to +1 scale or -3 to +3 scale. So it can read both positive and negative voltages. It has ranges from 3 microvolts full scale all the way up to 1000 volts DC full scale, both positive and negative. So there are 18 ranges on this instrument, very wide range of measurement capability with the DC Null Voltmeter. The HP419A was made from 1965 up until 1982. In 1965, it sold for $450, and in 1982, that price had risen to $1,550, which is approximately $5,160 in today's money. The HP 419A is still highly sought after and a desirable and still a very useful piece of vintage test equipment. And I'm very glad I got to finally purchase one from my lab. It's desirable and useful when it's working, that is. This one is not working. And so we are going to restore it, at least I hope. Hopefully we'll get to restore this instrument. So stay tuned for that. I have not plugged it in yet, and there's a reason why. I have thoroughly cleaned the exterior of the instrument. It had 60 years worth of grime and grunge on it, and took me about half an hour to clean the outside. And I've also opened it up, and the reason I've opened it up and looked inside because these instruments contain batteries, and I wanted to see if the batteries had leaked or if they had caused any damage internally, because of course it's 60-year-old batteries and we will have to replace them. Well, as it turns out, a previous owner already removed the batteries from this instrument, so there are no batteries in this instrument, and I'll show you that when we take the covers off. So it has no batteries. Now this instrument can be plugged in and also can be run completely on batteries, but it will not operate properly if you remove the batteries. So the batteries must be installed even when it's plugged in order for this instrument to operate properly. So that's the reason why I have not plugged it in yet and turned it on. So let's go through the front panel, some of the features of the instrument. First of all, I wanted to say that it has a basic accuracy of ±2%, right? When it's working, of course. But usually, as is typical with Hewlett-Packard instruments, their specifications are pretty wide. And in general, the precision and accuracy of all HP test equipment is far better than their published specifications. So I imagine it's got a far better than ±2% actual accuracy when we get this thing up finally working properly. Okay, so on the front panel, of course, we have the mirrored scale meter. We have the range switch with ranges from 3 microvolts all the way up to 1000 volts. The instrument can also be used as a picoammeter with a resolution of 30 picoamps on the lowest scale. It's basically like a galvanometer that they used in the old days. You can measure very, very tiny amounts of current with this instrument. It's a null voltmeter, and I'll show you that in a second. Let's take a look at the input. It's a banana jack input, plus or minus input, and a separate terminal for ground. So you can make floating measurements of DC voltage with this instrument. Off, there's a line indicator. When you select any of the other push buttons, the off button pops out and the line indicator will turn on whenever it's plugged in. Okay? When you select fast charge, it charges the battery at a more rapid rate. The instrument can't really be used when it's in fast charge mode. Battery test is just what it suggests. There's a range indicated on the meter for when the battery is sufficiently charged. It will be between the two marks indicated on the meter when you select the battery test function. When you select the zero function, an internal short is placed across the input internally, and you can use the zero control, the zero potentiometer control, to fine tune for a zero voltage center scale, zero indication reading. This is most important when you're down on the lowest ranges because it's a very sensitive instrument and you want to be as close to zero as possible. Voltmeter on ammeter mode is just what it looks like. This is the main function of the instrument, is as a standard voltmeter. It can measure very small voltages or very large voltages, anything in between. The input impedance of the instrument is 100 kiloohms on the lower ranges, and it increases to 1 megohm on the medium range, up to 10 megohms, and even 100 megohms on the upper ranges. The input impedance is 100 megohms on the voltmeter mode. It's a nulling voltmeter, so what we can do here is when we select the set null function, the instrument has an internal battery that uses a bucking voltage, which is adjustable by this null potentiometer, coarse and fine. There's actually two potentiometers built into this one knob. You can feel it change between the coarse control, and then you have a little bit of like backlash or hysteresis or something that's adjustable for the fine control of the null control. What that does is it adjusts the internal battery voltage to subtract from the input voltage, the unknown voltage across the input, and it's in the opposite polarity, so that you adjust that voltage until you read zero on the meter, and that voltage is actually the same, will actually be the same voltage as your input voltage. What that effectively does is allows you to not draw any current whatsoever from your source through the input terminals. So in that case, when you are using it as a null voltmeter, the input impedance is in fact infinite, not just 100 kiloohms or 1 megohm or whatever. It's actually an input impedance of infinity, which there are other ways to do that today, but back in the 1960s, there was only one way to do that, and that was with a nulling voltmeter. As you null the voltage of the input with the internal battery, you draw absolutely no current from your input source. That implies that your input impedance is infinite. That was very useful for Cal labs back in the 1960s because they used to use these to compare their reference voltages to a Weston standard cell, which is a battery, a special chemical battery that produces a precise 1.01830 volts. Exactly 1.01830 volts, but it can only produce that precise voltage when you are not drawing any current from that battery whatsoever. If you draw even a small amount of current from that battery, the voltage will no longer be accurate. And if you draw more than a small amount of current from that battery, such as a microamp or more, you in fact will damage the battery, and it will be permanently destroyed. So it's very important to not draw any current from a Weston standard cell. So that's what this voltmeter was used primarily for. Once you've set that null voltage to exactly counteract the input voltage that you're measuring, you select the read null function on the input terminal, on the front panel, and it will read the battery voltage that you just dialed up with the null potentiometer. And what that means is you will only draw current from the internal battery when you're making a measurement. You will never draw current from the input terminals. The input terminal will always remain as infinite input impedance when you have properly nulled this instrument. So that's the 419A front panel. Let's turn around and look at the rear panel. Okay, on the rear panel we have the old-fashioned oval style power cord socket. All right, that's not the standard type that we see on most modern equipment. This this style of power cord, the old HP style, was in use in the early to mid 60s, up until around 1960, I don't know, 68 or something like that. They used this power cord style. It has an input line fuse, 1/8 amp. I've already checked that fuse. It is the correct fuse. A line voltage selector switch, 115 or 230. It is properly set to 115 volts. We have an output on the rear panel. It's a DC voltage output, useful for driving a strip chart recorder or something like that. It's a -1 to +1 volt DC output that corresponds to the measurement on your front panel meter. And there's also an adjustment level control you can adjust with the screwdriver to calibrate that output level or adjust it. Serial number plate 532-00739. That implies that this instrument was made in around 1965, and its number 739 is one of the first ones HP ever made. This is a very old instrument. In fact, I know for a fact that it was manufactured in 1965 because there's a calibration sticker on the inside that says serviced by Hewlett Packard in 1965. So I can show you that when I get the instrument open. So that's the rear panel of the 419A. So let's open it up and I'll show you some of the circuitry inside and where the batteries are supposed to be and so on and so forth. I'll be right back. All right, so I removed the top and bottom covers and the two side covers, and there's still not much to see. There's an internal guard shield that basically completely surrounds almost all of the electronics inside. But the two screws on the top of that guard shield, and that comes off, and this is what I saw underneath. Let's see if we can illuminate it so you can read it. Serviced by Hewlett Packard Company, December 1965. Very interesting. I was in kindergarten in 1965. Very cool. Very cool. All right. I'm going to keep that. That's the one sticker that I'm going to keep on this instrument. There were several other stickers on the top and on the front that I removed and just got rid of because they were just gunking up the instrument, and who wants that? But this one is pretty neat, so I'm going to keep that. It's inside the instrument, right? It's underneath the top cover. And here we have the circuitry inside. Hard to see much of anything actually, but this is one of those instruments that has the now famous Hewlett Packard neon photo chopper assembly in it. Right here, the chopper block. And the neon light bulbs are mounted on a little circuit board that comes through this wire on the side and into the chopper block, and we'll show you those. But in all likelihood, those neons are probably, um, you know, beyond their useful life and should probably be replaced, but they're kind of tricky to replace. So we'll have to see how that goes. The function switch down on the bottom, the range switch over here with the precision resistors. Um, let's see what else is there to see. The power supplies on the rear panel behind this inner shield, so that any noise generated by the power supply, this is an oscillator that drives the neons. Any noise that's generated by that oscillator and in this power supply board is isolated from the sensitive input circuitry inside the shield. So this is behind that shield, right? And there's adjustments for the current for the neons and the frequency of the flashing neons. We'll get to that as soon as I get this thing up and running. Now the batteries are supposed to be down inside of here, but one of the previous owners had removed them. Luckily, there's the battery holder is still in there, and it rattles. I don't know if you can see it rattling around. And they had put electrical tape around the wires where the batteries are supposed to be soldered in place. So I'm going to have to come up with a solution to get batteries in here. The instrument will not operate without the batteries installed. And in fact, it's possible that you could even damage the instrument if you plug it in and try to turn it on without batteries in it. So hopefully all of that circuitry is still okay. But I'm going to have to put some rechargeable batteries in that circuit down there. Now there is the bucking voltage, the null battery, that is supposed to be down underneath here, underneath the photochopper board. And that would be on the other side of this hole here. Someone had rather clumsily drilled out the rivets that hold that battery holder in place for the nulling battery voltage. I'm going to have to come up with a solution for that as well, because that was originally a mercury battery, and you can't get mercury batteries anymore because they're toxic and they pollute the environment. They have other suitable batteries for use for this replacement for this battery. We'll have to come up with a solution for that, but I will do that as well. Let's see, what else is there to see? Going to be, my camera is not picking this up very well. But right here where my finger is pointing is I think it's a 15 turn pot for the zero control. It's 15 turns. You turn it 15 times for fine control of the zeroing of the instrument. And there is 2 pots over here under this side for the null control. There's a coarse pot and a fine pot, and they're both connected on a similar concentrically connected on one single shaft. So they're only controlled with one single knob, and I'll show you how that works as well. All the calibration trimmers for the various ranges. Amplifier circuitry is all on this board here. There's nothing really underneath on the bottom. On the bottom underneath, there's really not much to see, but I can take that cover off and show you that that's really just the function push button switches under there. And we'll probably see if we can't do some cleaning of those switches. Although a lot of this stuff is high impedance circuitry, shouldn't be really handling it with your fingers, because the oils from your fingertips can actually contaminate some of these high impedance areas and cause inaccuracies in the instrument. So it's best to use gloves when you're working on that kind of stuff. Use rubber gloves or something, or only touch the metal parts of the instrument, not the high impedance portions of the instrument. Um, in all likelihood, we will have to do some work on the photo chopper because those things are really tricky and touchy. But first, we're going to try to see if we can't get batteries to go inside the rear panel section over here. Hopefully, I can come up with a working solution to get batteries in there. So we'll see how that goes. So these are the batteries that I decided to buy to replace the batteries that are missing from the 419A. I bought four 6-volt battery packs. They're 700 milliamp hours each. Um, there were a couple of considerations when I bought the batteries. First of all, they had to be low cost, right? Which these certainly were. They're made in China. Um, I have used similar batteries to these before with success, and so I'm familiar with them, kind of. And secondly, I didn't want to go with a more modern technology than the tried and true nickel cadmium cells. So these are NiCads, um, mainly because I'm not a battery expert and I don't want to do a lot of research and engineering on the battery pack. It's a simple battery supply. Um, the other consideration, of course, is will they fit into the existing space? And that's an important consideration because the power cord on the rear panel, uh, the power socket on the rear panel extends into that space, and we don't want it to short out to the batteries, or we would see some arcs and sparks. And I'm yet to find out if they will fit in there, but I have a good feeling that they probably will fit. If not, I'll have to try something different. But this will give us the necessary voltages we need. I also wanted to make sure that the charging current on the batteries is appropriate for batteries like these. And so let's take a look at the schematic of the power supply and the charger circuit. That's under here. There we go. So the power transformer is over here. It's a very small transformer. Actually, the power supply is actually regulated by the batteries themselves. Um, this circuit is not really a voltage regulator per se. It is a constant current source for charging the batteries. And the batteries themselves are the main power supply of the instrument. So, um, when I take a look, we have a 6.81 Zener diode as a voltage reference here. We have a drop of um, zero point 0.7 volts across the base to emitter junction of the silicon transistor. And that remaining voltage, 6.81 minus zero point 0.7, is across the R3 560 ohm resistor. And that will set the charging current through this transistor, through the batteries, um, back to the common. Um, so if you do the calculation, that comes out to be something like 10.9 milliamps of charge current. That's in slow charge mode. Now, when the function is set to fast charge mode, here with this function switch S2E, it places this 750 ohm resistor R2 in parallel with the 560 ohm R3 and allows more current to flow through. So you get about 11, I'm sorry, you get about close to 20 milliamps, 19 point something milliamps flowing through in fast charge mode. Now these are 700 milliamp hour batteries, and um, so you're supposed to charge them at about 1/10 that rate, or about 70 milliamps. So even in fast charge mode, you'll only have about 20 milliamps of current flowing through. Um, Certainly won't damage the batteries. It may take an awfully long time to charge them up though. But the instrument in general draws such little amount of current that these batteries should last a very long time, even without being charged at all. Um, So I think we will be fine with this circuit the way it is. If I find that it's necessary to make a modification, I ought to be able to do that by maybe changing the transistor to a more sturdy one, or reducing the values of these two resistors to increase the current. Um, just do a calculation so I can get the current up to 60 or 70 milliamps. Um, and that's the recommended charging current for those batteries. But we'll probably just leave it exactly the way it is, because I imagine it'll probably work just fine. Okay, so I've removed the screws that hold the rear panel in place, and I can carefully fold the rear panel down to get access to the area where the batteries originally were located. You can see where the wires were soldered onto the original NiCad batteries, -12, ground, ground, and +12, like that. This is the battery holder where the batteries were originally located, and it bolts onto that rear part of the inner chassis. Remove those two screws, and you can see the the rear part of the battery holder is actually riveted to the rear inner chassis. So I'm going to have to drill those rivets out to remove this battery holder, and hopefully I can get 4 of these battery packs to fit in there without shorting out to the line cord socket, or the line fuse, or any of the other circuitry on the rear panel. I think I can get them all in there. I'm hoping that that's the case. Um, I also have noticed, if you look very carefully, there's some small amounts of corrosion, like right here where my little tweaker is pointing, and a couple of other spots in here where the batteries that were originally in there did in fact leak a tiny bit. There's a small bit of corrosion down here on the bottom of the aluminum in the shield, and also around this screw there's a little bit of corrosion as well. I can get that all cleaned up with a little bit of oh, I don't know, maybe just some isopropyl alcohol would probably be good enough to remove all that stuff, and make sure we've got good connections to all those points in there. I'll wire up the new battery pack and try to get them fastened in here after drilling out these rivets and removing this old battery holder. All right, so I've bundled up the 4 battery packs into one solid battery with plus, minus, and ground wires attached. Bundled them all up with electrical tape, and I've drilled out the 2 rivets that were holding the plastic battery holder in place for the original batteries. And now there's nothing left to do but to squeeze them in and wire them up and see if it works. Well, it was a very tight squeeze, but I did manage to get them tucked in down there, and attach them to the rear of the inner chassis with double-sided foam tape nicely and securely, and wired everything up and reattached the rear panel. So now the question is, does it work? Well, to answer that question, you're going to have to stay tuned for part 2. Sorry about that. Thanks very much for watching. Please like and subscribe, and stick around for the second part of the 419A restoration. Thanks again.